Good afternoon. It's a pleasure to be here and giving this talk. I'll be talking about thermonuclear supernovae and their use as cosmological probes, something that I've been working on now for the past couple of decades. So basically, what are supernovae? These are objects which are the death of stars, and there can be two kinds of stars which undergo supernovae. One is the death of very massive stars, and the other is when the white dwarf ignites and it explodes. So observationally, we see this as a new object popping up in the sky and a transient phenomena, and hence the name supernova. Nova is a new star. So as in everything, we try to classify them to understand the properties of these objects. And the basic classification is based on the spectral properties of these objects. The objects that collapse from massive stars, these are all the ones which are shown here in this box. And they are all the type, they're all due to the collapse of massive stars. However, this type here, what we call as the type 1A, these are due to white dwarf explosions, and they're also termed as thermonuclear supernovae. The basic distinction feature here is that the type 1A supernovae do not show hydrogen and helium features in the spectra, and they're dominated by the silicon features close to the light maximum. Whereas in the case of the core collapse supernovae, you have different types. The most dominant one is the one which shows hydrogen feature, and there are other types which either show no hydrogen but helium and silicon, or no hydrogen and no helium but only silicon. All these are indicative about the progenitor, and it also indicates the mass of the progenitor that explodes as a supernova. So the type 1A supernovae are the result of explosions of white dwarfs, and this was been proposed very early in the 1960s. And these actually occur in a binary system where the white dwarf can accrete matter and increase its mass. When the white dwarf approaches the Chandrasekhar limit, when it reaches a critical density and pressure, it can ignite the carbon and oxygen and lead to a thermonuclear runaway. So today, thermonuclear runaway in degenerate matter is widely accepted as the main mechanism for a type 1A supernova. So when the thermonuclear runaway happens, there's a shock breakout, and this shock period is for a very short duration. As shown in this plot here, the initial sharp rise, and then subsequently, as the matter begins to expand, it cools. But it is, during the thermonuclear runaway, there's a quick synthesis of elements, and you have the radioactive nickel being formed. And the further powering of the light is through the radioactive decay of 56 nickel to 56 cobalt, which takes about 8.8 days. And then further on, cobalt decays to iron. So this is what powers a supernova. So observationally, what we see is an initial rise in the magnitude of the object, followed by a decline, as shown here. Almost all supernovae have the same kind of variation in its light. And what we call as a light curve is nothing but the temporal luminosity, temporal evolution of the luminosity of a supernova. A spectroscopy of these objects can actually tell us about the stellar explosion and the elements that are synthesized during the stellar explosion. In the case of the thermonuclear supernovae, we have during the initial maximum, it's dominated by the silicon peak signatures. and also certain amount of unburned signature, basically unburned carbon and oxygen. And as the material expands and we begin to see the inner layers, the spectrum is dominated by the iron peak features. So here are some examples of observationally how we see the evolution of the supernovae. The pre-maximum spectra is almost featureless. It's dominated by the hot continuum. And as the material expands and the optical depth decreases, we begin to see the features more clearly. The features are broad, indicating the material is expanding at very high velocities. The typical velocities in the case of the type 1a supernovae is about 12,000 kilometers per second. So the explosion ejecta is expanding at such high velocities. And as I already showed in the previous slide, initially we see lines due to neutral and singly ionized intermediate mass elements, with some amount of contribution from the iron peak elements, particularly in the near UV region. And with time, the contribution from the iron peak elements increases, and by about 30 days, the iron 2 features begin to dominate. So in the nebular spectrum, we clearly see features of forbidden iron, that's doubly ionized iron and doubly ionized cobalt. And there is evidence of the supernova being powered by the radioactive decay of 56 cobalt to iron. So these features are very clearly seen in the spectra, which validates the theoretical assumption of the explosion being from that of a white dwarf. So how are they good cosmological probes? Supernovae of type 1a occur in all types of galaxies. They're extremely bright, and therefore they can be observed at very large distances. And hence they are standardizable candles that can be used as cosmological probes. Now, because the supernovae of type 1a are occurring on a white dwarf which is very close to the Chandrasekhar limit, what this means is that they all have a similar luminosity. The intrinsic luminosity is similar, because the mass of the object which explodes into the supernova is similar, close to the Chandrasekhar limit of 1.4 solar masses. So since the intrinsic luminosity is similar, what we observe as the apparent magnitude of the supernova being different is essentially due to the distance of the object. So hence we can use these objects to get the distance to the supernova. Once we observe the apparent magnitude, that is what we see, and you know what the intrinsic magnitude should be, so you know that the difference is basically because of the distance at which these objects are occurring. And that's the reason why they can be used as standardizable candles. Now, when we study the nearby standard candles, one cannot distinguish between the different models of cosmology. But however, when you go to the larger distances, the differences between these different cosmological models becomes more apparent, as shown in this plot here, as you go to the higher redshifts. So you can actually distinguish between these various models, whether the universe is accelerating or decelerating. These kind of information you can get as you observe further back in time. Now, how is it that we can use the supernovae as standard candles? Is that, as I said that earlier, we expect them to have the same intrinsic luminosity. However, there has been, observationally, we do find some differences. But what is also interesting is that these differences can actually be accounted for. The most famous relationship that one finds, or the correlation that one finds in the supernovae of type 1a, is that they have very similar light curves, and the absolute magnitude that you see at maximum is very tightly correlated with the initial rate of decline. So this is called as the luminosity width relation, which was first shown by Phillips in 1993, where he showed this relation with just about 9 well-studied supernovae. Now, accounting for this differences in the width and correcting for that using what we call as the stretch factor, you can see that all these various supernovae which looked very different, the light curves all appear to be exactly the same. Okay? These are actual observations, the light curves from observations of supernovae. So therefore, thermonuclear supernovae are excellent standardizable candles for measuring the cosmic expansion. So what is the key result that one has obtained from the supernovae by using them as cosmological probes? As most of you are aware that in the year 1999, the 2000, I think, the Nobel Prize was given for the study of use of supernovae, and the result that they obtained, that the presence of dark energy and that the universe is actually expanding faster than what we thought it was. Okay? So this is a key result that was obtained from using the supernovae as cosmological probes. So essentially what was observed is that the distant supernovae, that the ones at the higher redshifts, particularly at the time when this study was done, which was what gave rise to the Nobel Prize, there were two different groups which are studying supernovae systematically, doing a systematic survey of supernovae and observing these type 1a. Both these groups at that point of time studied the highest redshift supernova known then, which was about 0.7, just at the border where one could distinguish between the different cosmological models. Today, the most distant supernova known, for example, is about 2.7 or something like that. Now, this plot here shows up to 1.7, where you have that object known to be a confirmed type 1a supernova. So what the distant supernovae have indicated is that they are much fainter than expected. So this essentially means that the universe is expanding, or rather accelerating at a rate faster than what we expect, what was expected. Okay? And this acceleration is actually explained through the presence of something called the dark energy. And this dark energy, the 70% of the universe is filled with dark energy. So this is what supernovae showed. But however, one thing that is there with the supernova observations is that the accuracy of these observations is about 6%, and one has not been able to make it better. And that is basically because of the diversity that one sees in these objects. Now, what I have plotted here is the phase space diagram, which is essentially an expansion of the Phillips relation, which was first formulated in 1993 with just about 9 objects, which showed an excellent correlation. But in the past couple of decades, with the dedicated surveys for observations of supernovae, we find that you see this phase space diagram shows a whole lot of variety in these thermonuclear explosions. And what is seen is that only about 64% of the type 1a supernovae follow the luminosity width relation, 20% are overluminous, 16% are subluminous, and then we have another very peculiar class which you call as a 1ax, which does not follow the width luminosity relation. And this diversity is also seen in the spectral properties, in the spectral features. Some of these diversity that one sees in the spectra are actually correlated with the light curve. For example, there's a diversity in the strength of the silicon features and the expansion velocities, which is very well correlated with the light curve. So we see weaker silicon in the brighter events, and the velocities are higher in the fainter events. And there is some other diversity which is not necessarily correlated with the light curve. There are some high velocity components seen in some supernovae, but not in all of them. Like for example, some supernovae show a high velocity calcium component, particularly seen in the pre-maximum phase, whereas several of them have also shown signatures of unburned carbon. So what is this diversity due to? It's basically due to the nature of the progenitor. The progenitor can either be a single degenerate white dwarf in a binary, or it can be double degenerate, that is two white dwarf, a binary system consisting of two white dwarfs. The other property which can have an influence on the diversity is the metallicity or the environment. It's generally found that the type 1a supernovae that occur in spiral galaxies are brighter than the events that occur in the ellipticals or in the bulges of the spirals. Another factor could be the angular moment of the white dwarf. I mean, if the white dwarf is rotating, then you can have a slightly massive white dwarf. The white dwarf can survive beyond the Chandrasekhar limit. And in that case, it will be a superluminous supernova. And the explosion mechanism itself, there are different explosion mechanisms which have been proposed. It's either deflagration or detonation. The explosion itself can occur in a spherical manner or asymmetric. It occurs in just one location. So a lot of factors which can cause the diversity. And of course, these peculiar cases, as I mentioned earlier, these are underluminous events which have a decline rate similar to what we call as the normal type 1a supernovae. Their pre-maximum spectra are very similar to the overluminous events, but they have extremely low expansion velocities, almost a factor of 2 lower than the normal type 1as. These are termed as the type 1ax. And initially, there were very few such objects known, but today there are more than 20 of these objects known, and we only expect that as we get into larger surveys, these kind of objects will increase in number. And we don't know the population of these objects at the higher redshifts are not very well known. So as we go deeper in the surveys, the number of such objects that would be detected could be more, and they would certainly cause a problem in using supernovae as cosmological probes. A little bit on the various explosion mechanisms. The explosion can be a pure detonation, where you have the burning front which propagates at supersonic velocity. A detonation mode of explosion will convert the entire white dwarf into 56 nickel. So it's practically the entire white dwarf is burnt out. But however, the theoretical models have not been able to produce the intermediate mass elements which are predominant in the spectra. The other model proposed is a slow burning, the deflagration wave within the white dwarf, where the burning actually propagates at subsonic velocity with respect to the unburned material. So this kind of a deflagration creates the IMEs, but it also overproduces 56 nickel, and there's a lot of unburned material which is present. The most successful model has been the deflagration to the detonation transition, the DDT or the delayed detonation model, where the explosion actually begins subsonic as a deflagration wave, and then upon reaching the supersonic speeds, it leads to the detonation of the white dwarf. So these models have actually been able to produce the observed properties of several supernovae. Coming to the progenitors themselves, they are primarily a white dwarf in a binary system, and the binary itself can be a single degenerate where you have a single white dwarf which is accreting matter from a normal star, which is typically a giant. Or it can be a binary system with two white dwarfs which merge and give rise to the supernova. So there are a variety of progenitor models that can explain the observed explosion characteristics. And there are some, like for example, I said earlier itself, if the white dwarf is rotating, you can give rise to these overluminous systems. The double degenerate progenitors, again here there are different kinds of models which indicate the kind of mergers which can happen. One is the merger of, it's a violent merger of the two white dwarfs. These models predict slow decline, which essentially means a broader light curve. And they also predict slowly declining velocity evolution and mixed carbon and oxygen layers. So in this case, there is a lot of mixing of the various elemental regions. The other model is having a head-on collision of two white dwarfs. In this case, the ejecta is stratified with carbon and oxygen in the outer layers, silicon in the inner layers, and nickel in the innermost layer. One can also have, the merger with the secondary spiraling into the primary white dwarf, and the instabilities, created while it is spiraling in can actually lead to the burning of the primary white dwarf and the supernova. In the case of the single degenerate progenitor, you can have a carbon-oxygen white dwarf igniting due to the DDT phenomena, and this is the model which explains single degenerate scenario the best. Now, as an alternative, one can also have a sub-Chandrasekhar mass white dwarf with a helium star companion, and the explosion actually will occur in the helium shell that is accreted. So the burning first begins in the helium layer, and then it propagates onto the carbon-oxygen core. So this kind of burning will actually give rise to a subluminous explosion. So these are the various kinds of progenitors and the explosion models which have been proposed to explain the diversity that is seen in the type 1a supernovae. So what we have been doing is that we have been studying low redshift supernovae to understand the diversity, so that the understanding from the low redshift supernovae can be transformed to the ones at the high redshift. So basically, we do a detailed study of these low redshift supernovae, typically monitoring them for more than a year or so. And these studies, we have been undertaking these studies using the Himalayan Chandra telescope. There are several supernovae that we have observed in the optical, and we have supplemented our data with multi-wavelength observations from other facilities. So the plot here shows the various kinds of, the different supernovae that we have observed with the HCT so far since 2003. And as you can see, we span almost the entire range of the thermonuclear objects that we know today. So what we do is that we study the light curve and the spectral evolution to estimate the explosion parameters. The theoretical models are fit to infer the explosion mechanism and the nature of the progenitor. So a few examples in the studies of the diversity. In the normal type 1a, we have seen objects which have shown high velocity calcium components. We have seen objects with signatures of unburned carbon in quite a few of them. And in fact, using radiative transfer models, we have also been able to estimate the mass of the unburned carbon in one specific case. A very interesting object that we recently published is the supernova which occurred in the year 2011. This supernova had a very slow decline, but its luminosity falls under the normal type 1a supernovae. It is in fact the slowest declining type 1a supernova known till date. The peculiarities that we found in this object was that the unburned carbon was at a lower velocity than the silicon layer, which essentially meant that there was a lot of unburned material inside of the silicon layer. And also, when we fit the analytical model to the bolometric light curve, we found that the mass, ejected mass, is about 1.9 solar mass, which obviously is much higher than a single white dwarf. So this necessarily had to be a merger of two white dwarfs. And the best model we found was that due to violent merger of white dwarf with the masses of the two components being greater than 0.9 solar masses, this was what we found could reproduce all the observed properties, that the broad light curve and the slow velocity expansion, as well as the presence of unburned carbon in the inner layer. So here what is essentially happening is that the primary is, it detonates, and then the burnt material engulfs the secondary, which still is not fully burnt, and hence you find unburned material, carbon and oxygen in the inner layers. The other kind of objects, the type 1AX, the other objects that we have been studying in detail to understand the diversity. As I mentioned earlier, these are the fast declining but low luminosity and low velocity objects. So far we have been able to study about 4 or 5 such objects, and all these objects we have been able to explain as occurring in a single degenerate progenitor, where the explosion actually happens by deflagration and not by the delayed detonation method. So now we are also trying to look at the similarity between the different types of 1A explosions. And this is the work of my PhD student. So what he is doing is that he is concentrating on 5 supernovae, all of them normal type 1A. As you can see from the light curve parameters, they follow the width luminosity pretty well. And they all have common spectroscopic features, in the sense that these are bluer objects, that is, they're slightly hotter than the normal 1As. And all these have unburned carbon in the inner layers, which indicates there's a mixing. So what he has done is that he's trying to understand the variation in the observed width and the peak magnitude in terms of the white dwarf masses. We are assuming that all these are coming from the violent merger, because it's a violent merger model which very clearly predicts the presence of unburned material in the inner layers. So light curves and spectra of these objects are being simulated using the 1D analytical density profile by varying the mass and the kinetic energy. And the idea is to constrain the progenitor masses, the total mass of the two white dwarfs. And also get the differences in the abundances for each of these supernovae, and probe the distribution of carbon in the ejector. So about 36 model light curves have been generated with spherical averaged one-dimensional abundance distribution under the violent merger model. And also the model spectra have been generated, and find that the observed properties are well correlated with the white dwarf, the total mass, the total ejected mass, kinetic energy of explosion, and the abundance stratification. So basically such studies will enable generating a family of light curves that can be used for better understanding of the high redshift objects, and also reduce the systematic errors in the use of supernovae of type 1A as cosmological probes. So I just conclude with some final thoughts. We know now today that supernovae of type 1A are excellent probes in cosmology. And there are clear evidences that there is no single model which can describe all supernovae of type 1A. Both the single degenerate and the double degenerate channels are likely. The current and future dedicated large surveys are providing, and will also provide, an excellent database of these objects, which will enable us to study the subtypes using large samples. And combined with the progress in theoretical modeling, serious progress is being made in understanding almost every aspect of these objects, right from their explosion physics to their progenitors, and thereby their use as standard candles. So supernovae in the future will very well become the key to unlocking the darkest secrets of the dark energy, as mentioned by Andy Howell. Thank you.
Thank you, Professor Anupama, for this interesting talk for very fascinating objects in astronomy. So, any questions? Yeah. Yeah, hi there.
Yeah, actually, so when these results were first announced, there was just one object. Now they have a few more with the redshift going up to 1.5, but clearly the number of objects are not really that higher number. But the fact that the results you're getting from the supernova observations are matching very well with the other modes of observations like the WMAP or the Planck observations indicates that what results one is getting from the supernovae are it's consistent with the other observations. In the future surveys, and of course the supernovae that one would observe with the JWST, which can be done at extremely high redshifts, we need to see what they would say.
Okay. Any other question? Okay. If there are no other questions, thank you very much, Professor Anupama, for that talk. So we come to the close of this session today. Dr. Nautiyal, is there anything that you would like to say?